Okay guys, so we are looking at the Wednesday, September 21st notes. I'm going to work through them up here so that I can post them for people who are absent, or if you just need to look over them again, you can look on Canvas and re-watch some things you may need help with. Alright, so for number one, to start with though, is talking about that when we are trying to find a limit, C is an x value that the function is approaching. Notice x value. L is defined as the y value that the function is approaching as x approaches C. The first thing that we try to do to evaluate a limit is we want to just try plugging it in. If I plug 2 in here, I'm going to have 2 squared, which is 4, 3 times 2, which is 6, plus 2. On the bottom, 2 minus 2. So I'm going to get 0 over 0. When we get 0 over 0, that means that there is probably going to be a limit. So when we get 0 over 0, it means there may be a limit, and we have to do more work. Do more. See those zeros there, basically? So do more work to figure it out, because there might be a limit there. So one way that we can do more work is we can just check on the graphing calculator. We can just get as close as we can to 2 without being equal to it. So turn on your graphing calculator, go to y equals, and put the function in. So the function is x squared, and I need that in parentheses, x squared minus 3x plus 2. All of that needs to be in parentheses, divided by x minus 2. So we have that in parentheses. Oops, I forgot my parentheses on the top and the bottom. Okay. And so now we're going to do a zoom 6 to see it. And it looks like a line. We may not have been thinking that it would look like a line with the x squared. So we're going to investigate, why does it look like a line? I'm going to try just plugging in the number 2. Second trace, calculate a value when x equals 2. And it gives me no y value. Okay, so something's going on there. And what's going on is that there's actually a hole in the graph at 2. But that does not mean that we don't have a limit. There is a limit there. So to find it, I'm going to do second trace, calculate a value when x is 1.999. And there's the answer I get. I'm not going to bother checking the other 2 because I want to be as close as I can to 2. So now I'm going to check something else very, very close to 2. So I'm going to check 2.001. And I get this answer, 1.001. So what is the y value we're converging on as we get x closer and closer to 2? What's it going to be, guys? What's the limit going to be? 1, yes. So the limit equals 1. So even though we got 0 over 0, there was a limit that we could find, and it was 1. Now, for this part, it says write a simpler function that agrees with the given function at all but one point. So this ended up being a line with a hole in it at x equals 2. So if I want a simpler function, here's what I can do. I can factor this. So this is going to factor down like this on the top. On the bottom I have an x minus 2. It's going to have to cancel out. So I know one of my factors is going to have to be x minus 2. I put my x. So I'm thinking x times x is x squared. That works out. 1 times 2 is 2. And this is going to have to be a minus in order to factor that. Now my x minus 2's cancel out. And here would be my simpler function. So if I have the limit as x approaches 2 of x minus 1. X minus 1 is the simpler function. And what would we get now if we just plugged in the number 2? 1, right? So that's another way we can find a limit. We can do it graphically, by creating a graph and plugging in numbers really, really close to what we're trying to be equal to. This is called an analytical method. So to find a simpler function, we just try factoring. Okay, let's look at number 2 now. I try plugging in 0. If I plug in 0, I'm going to get 0 on the top. 0 plus 1 is 1. Square root of 1 is going to be 1. Minus 1 is going to be 0. But 0 over 0 does not mean that there's no limit. We want to do some more work. So we're going to check it on the calculator to start with. So it's x divided by the quantity, square root of x plus 1, minus 1. I'm going to graph it. The question is, what is y approaching as x gets closer to 0? I'm going to try just substituting in the number 0, but it tells me that there's a hole in the graph there. But a limit just means what are we getting closer and closer to. So we're just going to check these two numbers right here that are very, very close to x equals 0. So I'm going to do second, calculate a value of negative 0.001, and we get this, 1.999. Just to double check, we'll see what happens if we put in positive 0.001. And if we type that in, we get 2.0005. So what is it then? What's the y value we're approaching as x gets closer to 0? 2. So the limit here would be 2. Okay? We're going to do one like this later. I'm just going to tell you the method that we would use to simplify this would be to multiply by the conjugate of the denominator. Whenever we see radicals, we want to use conjugates. Do you know what I mean by a conjugate? Who can explain it? Paige, you said yeah. What do we do? Right. So for this one, it would be the square root of x plus 1 plus 1. That's what I would have to multiply by on top and on bottom. We're not actually going to do it for this one, but we would not distribute through the top. We would just keep that in factor form, but we would distribute through on the bottom. Okay. All right, so for this one, we're going to graph this. This is saying we're graphing the line y equals x minus 2. What's the y-intercept there, guys? Y equals x minus 2, the y-intercept is negative 2, and what's the slope? 1. So I'd go up 1 over 1. So we're going to graph that. But it says that we're only graphing that when x is not equal to 3. If x does equal 3, then we're supposed to plot the point y equals 4. Y equals 4 would normally be a horizontal line, but in this case we're only doing it when x is 3. So what happens is there's a hole in the graph here when x is 3, and we're supposed to plot the point 4. So this is the way the graph should look. So now using this to find the limit. See, most people would say the answer to this, the limit of f of x as x approaches 3, they would say the answer is 4 because of that dot. But that's not what a limit is. A limit means as we approach 3, from both the left and the right, what is the y value that we're approaching? What's the y value right here that we're approaching? 1 is correct. So this limit is 1. Because a limit just means the overall trend of the graph. So if I'm thinking of this as being the whole graph, the trend as we approach 3 is that the y value is approaching 1. That's what we would call almost like an outlier or a distractor. That's not going to be meaningful based on the rest of this graph. That's the one that's important, the trend. As we approach 3, we're approaching a y value of 1. Okay, now, what happens if we don't have a nice graph where we're approaching something specific? That's what we're going to look at in the next one. So we're going to use our graphing calculator to find this limit. So go to y equals, clear out what you've got, and put in the sine of 1 divided by x. And when we put in a sine, cosine, or tangent, we want to do a zoom trig to see it. Here's how it looks. Okay, let's help it. Okay, we're trying to put this in here. Is there anything else in there? Let's do a zoom trig one more time. There we go. Okay, so that's the way the function looks. Now, what the problem is saying, what is the y value as x approaches 0? Look what's happening here. As x approaches 0, the graph is going back and forth, back and forth. It's oscillating very quickly. I'm going to get in very close here. I'm going to make my x min like negative 0.2, and my x max positive 0.2. My x scale, I'll make it just 0.1. So that is really close in there. That's really close to 0. And look what happens. Is there any one specific trend here that's happening? No. This is jumping all over the place. Think of this as like a heart monitor. We're going da-dum, da-dum, da-dum. And then all of a sudden right here as you get close to 0, it's just so sporadic. When a graph looks like that, we have to say that this limit does not exist. Because as we approach 0, that graph is not approaching one specific number. In fact, I could get in so close, I could go like between negative 0.001 and positive 0.001. So between 100th of a second, if we're thinking of that kind of like heart monitor problem, just kind of watch this. See, we're zoomed in there so close, and look what's happening to the graph. It's doing all of that. So there is no limit there. All right. The next graph. This is the absolute value of x minus 3 over x minus 3. So we're going to try to graph this. I'm going to make a chart of values. So if I let x be, say, negative 2, negative 1, 0, 1, 2, 3, 4, 5, just kind of getting a feel for what's going on here. If I plug in negative 2 minus 3 is negative 5, that absolute value is 5. Negative 2 minus 3 is negative 5, that's going to be negative 1. I plug in negative 1. Negative 1 minus 3 is negative 4, absolute value is positive 4. Negative 1 minus 3 is going to be negative 4, so I get negative 1. In fact, what we're going to see is that all of these are negative 1. Until I get to 3. 3 minus 3 is 0. 3 minus 3 on the bottom is 0. So right here at 3, something weird is happening. So I'm going to put an open dot there to denote that. Check 4. 4 minus 3 is 1. 4 minus 3 is 1. So that's going to be 1, 1. So here is the way this graph looks. At 3, down to the left, the graph is always going to be negative 1, like this. At 3, down to the right, it's always going to be positive 1, like this. And what happens is there's going to be an open dot. See, this is always going to be negative 1, and then when we get to 3, then we have this weird thing happening here. You can look at it on the calculator. We can go to math, num, absolute value of x minus 3 divided by x minus 3. And then just do a zoom standard, a zoom 6. And it shows you how it looks. So if we are thinking of the limit as x approaches 3, we are not approaching one specific number. As we approach 3 from this side, I'm approaching 1. as I approach 3 from this side, we're approaching -1. So what do you think the limit is when that happens, when it's not one specific number? What do you think we say about the limit? Somebody whispered it. We're going to say then that the limit does not exist. So here, the limit does not exist. So when we have a big gap like that, that's another time the limit does not exist. When we had that graph that was so sporadic like that, that was another place the limit does not exist. All right, the nice thing about limits, we have some theorems and properties on page 57, but the nice thing is that you pretty much do what you would think you would do. So if we have a 4 inside of here, we can basically factor that out to the front. There's a property on page 57 that allows us to do that. So in this problem, we are given the limit as x approaches c of the function is 3/2. And the limit as x approaches c of g of x is 1/2. So for f of x, the limit is 3/2. For g of x, the limit is 1/2. So if we're doing this, all we have to do is substitute in. It's going to be 4 times, and then we have to look for this limit, 3/2. And so we're going to get 12 over 2, so this is going to be a 6 for that limit. So what would you think we would do here then, if we have the limit as x approaches c of f of x plus g of x? What do you think we do with these two limit values? What do you think? Just add them, right? That's all you have to do is just add them. So I have to take the limit for the f of x, which is 3/2, plus the limit for the other one, which is 1/2, and so that answer is going to just be 2. What do you think we do for this one? Just what, Casey? Multiply the two limits. So we're going to look at the limit of f of x as x approaches c, and we multiply it by the limit for g of x as x approaches c, and we get 3/4. Last one here, division, just divide the values. 3/2 divided by 1/2. What's that going to be, everyone? Just 3. Multiply by the reciprocal. Okay. So these are our methods for solving limits analytically. Again, we have 3 ways to solve limits. One's numerically. Numerically means you just plug in the number and get your answer. The other way is analytically. Analytically means use algebra. And the last way is graphically. Graphically is where we can look at the calculator and look at the graph and kind of see what the limit is. So first thing we always want to try, number 1 method, is to try just plugging in the C value. That's the number 1 thing to try. If that doesn't work, then you want to try one of these 3 things. So, let's look at example 1. First, we're going to try to plug in 0. I get 0 minus 0 over 0. That gives us 0 over 0. Does that mean 1? No. It means we have to do more work. So anytime you see 0 over 0, you're going to have to do more work. So we're going to try one of these 3 methods. Let's try factoring. So I'm going to factor an x out of the numerator, and then I'm left with x minus 5 over x. And now we can cancel these out. So whatever we canceled out, that means there's a hole in the graph right there. And whatever makes that 0. 0 makes that function 0 in the denominator, so there's a hole there. But just because there's a hole there still will be a limit. So we're going to plug in our 0. 0 minus 5 is negative 5, so that's what the limit's going to be there. So we don't even have to look at the graphing calculator because we can do that problem very well analytically. with algebra. Number 2, first thing we always try to do is plug in our C value. I'm going to get x plus 0, that's x squared minus x squared, that's 0 over 0. Have to do more work. So I can't factor this. I actually could, but it's not going to be helpful. So when this happens, I might just want to multiply out the factors. Because if I multiply this out, it might get easier. So I've got this. I'm going to square this. This is x plus delta x times x plus delta x. I can't just square each one of those. I have to FOIL it. So I do my first times my first is x squared. The outers is plus x delta x. The inners is plus x delta x. The last times the last. Delta just means the change in. So this is all one term. Delta x times delta x is delta x squared. And then I have to write my last one, which is minus x squared. So look again at what we did. We squared this by doing the first, outers, inners, last. That's all of this. And then I had to put minus the other value. So simplifying this now, what's x squared minus x squared? What happens with that? Cancel out, right? Okay, so now I'm going to have this. All I have are these terms. So what's x delta x plus x delta x? 2x delta x, right? Our goal is to be able to plug in 0 for delta x. But if I do that, I'm still going to get 0 over 0. That means I still have to do more work. What can we factor out of these two terms? Alright, so we're going to take out a delta x. And we're left with 2x plus delta x over delta x. And so now our delta x's cancel. And we can finally plug in 0 for delta x. 2x plus 0 is just 2x. See, we always have a limit until we're finally able to plug in whatever this is down here. Once we substitute that in, then we say that is the limit. All right, example 3. We try plugging in 0 for x. I get radical 2 minus radical 2. That's 0 over 0. Do more work. I can't factor. Multiply by the conjugate. This is what we're always going to use if we have radicals. So if we have radicals, we're always going to be thinking conjugate. So to multiply by the conjugate, everything stays the same except for this middle sign. If it's a minus, it becomes a plus. If it's a plus, it becomes a minus. The reason why we want to do that is because we want the outers and inners to cancel out. And if one of them is positive and one of them is negative, they're going to cancel out. So whatever we multiply the top by, we have to multiply the bottom by. Okay. So now we've still got our limit. We haven't substituted in. We do the first times the first. What's that going to be, guys? Just 2 plus x. Good, the radical just goes away. I just told you that when we multiply the outers, we get a positive radical 2 times 2 plus x. The inners, we get a negative 2 times 2 plus x. Those are going to be 0. So I'm going to go to the last times the last. What's negative radical 2 times positive radical 2? Minus 2. Yep. On the bottom, you will never multiply this out. Unless it's conjugates. If it's conjugates, you want to multiply it. But if they're not conjugates, you want to leave it factored. Otherwise, it's going to make the problem more difficult. Just leave it factored. So on the top, we have 2 minus 2. That's 0. So now we have this. Our whole goal is to be able to get rid of the fact that we have 0 over 0. So now I have x divided by x. Those can cancel out and give me just a 1. That's good, because now I can plug in 0 for x. So I have a 1 on the top. If I plug in 0 for x, see, 2 plus 0 is just 2. So I've got radical 2 plus radical 2.